Fantastic. Welcome everyone. Good afternoon and welcome to our second show and tell session at the Strategic Innovation Fund. This session is called Improving Resilience Using Multi-Energy Systems. I'll give a little bit of context to that in a few minutes, but first I'll just do a brief introduction to the SIF for anyone joining who's not familiar with this program. So the SIF, which stands for the Strategic Innovation Fund, it's a £450 million fund paid for by the consumers, and it funds projects which align to our two main objectives: deliver net zero at the lowest cost to the consumer, and place the UK as effectively the Silicon Valley of energy system innovation. So it's funded through the RIIO-2 price control, and it's a collaboration between Ofgem and Innovate UK. And all the projects are led by energy networks. And within the projects, there are project partners from different technology providers, SMEs, and various other businesses in the UK. So the program operates in a three-phase model. So we start with discovery, which is a 3-month feasibility sort of study phase. Then we move on, if successful in discovery, they're invited to apply for alpha, which is a 6-month phase where we look at testing some of the solutions that they've developed to the energy network problems. And then if successful through alpha, they can apply into beta, which is our really chunky phase. It's a 3-year phase, and we look at the sort of rollout and commercialization of some of the solutions developed in these projects. So for this round 2, we had 53 projects funded over 3 months. And today in this session, this afternoon, we're going to look at 5 of them, which cover that multi-energy system aspect. So a little bit of context to this particular sub-theme. Well, according to the Climate Change Committee's, the Climate Change Committee, low carbon energy generation needs to increase first by double, then triple, then quadruple, and then it needs to multiply by 5 by 2035. So the level of new energy generation being added onto the systems is quite staggering, and the amount of infrastructure that's needed around that, not just from an electricity point of view, but also from gas as well, it is enormous. We're looking at increasing electricity cables by 49%. So it's by 2035, it's quite staggering. And then from a gas perspective, the National Grid future energy scenarios predicted that there would be somewhere between 174 and 474 terawatt hours of additional demand added on to, in terms of hydrogen by 2050. So the feat of engineering required is enormous, but also adding on to that, we need really resilient systems. And it's not just going to be a one system problem. It's not just going to be a problem which is addressed by the electricity system. It's all networks, all systems working together, which is why it's really nice to see these 5 projects addressing that particular area. And what's also really nice about this show and tell is that we have 5 completely different networks leading each of the projects as well. So it really shows that we're working as a unit in the UK to address some of these resilience issues. So in terms of housekeeping, we're going to have 5 presentations today. We'll have a 10-15 minute break after the 3rd presentation, about halfway through, maybe an hour or so into the show and tell. I would ask, if you have any questions, please pop them in the Q&A box, not the chat. If you pop them in the chat, we won't be able to see them. The chat is for your networking. So, please feel free to introduce yourselves in the chat, but any questions, please pop them in the Q&A box and we will pick them up in the assigned Q&A sessions for each of the projects. And it doesn't necessarily have to be a question. You could just ask for a bit more clarity on certain aspects of the project, or if you're also involved in some of these projects, you might want a bit more clarity on where there's overlap or where you could collaborate or work together. So I'm really, really excited to see some of the input from the audience as well. So I think we have everyone here ready to present. Next slide, please. I'll just quickly run through the agenda. Next slide, please. There we go. So we're going to start with REWIRE, which is a residential whole system integrated resilience, and that will be led by Electricity Northwest Limited. We're then going to follow it with a Q&A, and then we'll lead on to the whole energy system resilience vulnerability assessment, also known as wellness, which is led by National Grid Electricity Transmission. We also have a really interesting project by Northern Gas Networks, which is called HyCoRe, which is looking at hydrogen cost reduction. Again, talking about that additional forecasted demand we are expecting on the network and how do we make hydrogen accessible for the future. We're going to have a 15-minute break, and then we're going to look at NextGen Electrolysis, bringing wastewater and turning it into green hydrogen. That's being presented or led by Wales and West Utilities. And then finally, to close the session, we have Distributed Network Information Modelling, DNIM, led by Southern Gas Network. So we have a range of utilities here to present their resilience projects. So without further ado, I'm going to hand over to our first project, REWIRE, which is led by Electricity and Northwest Limited. Over to you guys.
Hi everyone, I'm not actually Victoria, I'm Nick Howers from Fraser Nash Consultancy. Victoria's been dragged away, I just cover for her for this project. You go next slide please. Oh, and again. So what we're going to quickly run through here is the problem and the project summary, a headline of the key messages, summary of what we've done in each of the work packages, including what the activities through discovery and the benefits we found, and how our thinking has evolved during that process, and then quickly look ahead to where we go next. Okay, so next slide, please. So the problems, I think, as was just briefly sort of highlighted, there is a growing generation from we are growing the capability of generation from distributed energy sources and electrification as part of the decarbonisation process. But at the same time, we are curtailing the use of renewable energy when it's available, because actually the demand is quite often low at the same time. So what we're trying to look at in this project is where we can store that energy in a green and effective way. So the proposed solution, REWIRE, is looking at using energy or improving energy system resilience through the use of innovative domestic level multi-energy systems. Next slide, please. And what does that actually mean? Well, you kind of got two key scenarios here on this slide. So the one on the left is kind of a typical winter scenario. So you've got high demand but low generation from solar, typically solar, but also sometimes wind energy. Conversely, the diagram on the right shows you a kind of typical summer day where you've actually got relatively low demand for energy, but there's a particularly high amount of it generated from renewable sources. So what we are looking at in this project is whether it's technically and economically viable and also beneficial to the energy network to integrate vector conversion technology, meaning the conversion of electricity to gas, in this case hydrogen, and back again, but to do that at a domestic level to support both national and local system resilience. Next slide, please. So headlines of what we discovered. So key point is that if you are starting to use hydrogen as a key energy source, having a hydrogen network massively increases the feasibility of this solution. That's generally due to a limitation on the domestic storage that you can achieve of hydrogen, and also electrolyzers are not typically available at a small domestic level scale. We are using a fuel cell, and if you were to use that fuel cell as a combined heat and power unit coupled with some thermal energy storage, this makes it a very effective solution. So it actually allows a domestic property to generate both its electricity and its heat from the fuel cell, and then the thermal storage allows the property to then store that heat to reuse it at a time when it's needed. And in this case, you end up with a very comparable payback period for the domestic homeowner compared to a kind of typical heat pump and Tesla Powerwall battery system. In our solution, excess solar PV generated by each property can still be converted into hydrogen if the hydrogen network has large-scale electrolyzers, so excess energy is transferred back to the electricity grid, which can be turned into hydrogen. And it does have the solution, or the solution has the potential to offer significant increases on the electricity and gas network resilience due to the link between the two, which is something which currently is very rare, if present at all. Work package 3, which was carried out by Imperial College, we'll come on to in a bit more detail, but they analysed at a whole system UK level and found significant benefits across the system of around 15 gigawatts if a 10% domestic deployment was achieved, which is equivalent to just under £3 billion a year. And lastly, the preliminary analysis showed that rural areas are most at risk of electricity outages. In ENW's region, the rural areas where more than 75% of customers have a gas connection is about 10% of their total. And aligning that gave some very significant benefits to those properties. It's worth noting, though, that that doesn't mean that it would limit the deployment to rural areas. It's just that's where it gave particular benefits in terms of the resilience. I think the next slide, and we'll move on to Harry to talk about the work that was delivered in each of the work packages.
Yeah, cheers, Nick. So the first work package was included a technology viability assessment, which itself was including a preliminary literature review into what's available on the market right now. As well as that, it included a financial viability assessment. Specifically, that was a return on investment analysis for a prospective customer of a REWIRE technology, as well as a simulation of a property throughout the week in terms of demand and storage. The key findings of this work package, this were very important, basically, specifically that directly replacing a house battery scenario in a fully electrified house with electrified heating was not feasible because of the lower efficiencies of hydrogen conversion technologies compared to the round-trip efficiencies of a battery. As you can see in the diagram on the right, where the red bar represents that option 1. But what was found in this stage was that if we were to oversize the fuel cell and then use the waste heat from that fuel cell to charge a thermal store, the return on investment period actually became more favorable than a battery solution, even though the CapEx investment did become larger because of this. Challenges identified in this stage, not too surprising, was component sizing and technology readiness levels for fuel cells, electrolyzers, and reversible fuel cells at domestic scale. And then also the question of how to design the system control logic, and should that benefit the network or the consumer, or can it benefit both, basically. So we go to the next slide. Work package 2 was looking at the network perspective and seeing if there were any patterns of geographic distribution of network archetypes that best suited this solution. This included analysing low voltage outage data reported by ENW, actually, and correlating this with demographic and various geographic, I'd say, characteristics reported at an LSOA level by the UK government. One of the key findings here, not too surprising, I don't think, that rural urban classifier is a high predictor for low voltage outage risk, with rural areas tending to be more at risk than urban areas. And then also, if we take our findings from work project 1, which told us that a hydrogen network was required to make the solution feasible, if we then add the additional filter that the the network needs to have a large portion of on-gas customers to reuse the existing gas infrastructure. That does reduce the number of highly feasible, highly suitable areas available to us. Bear in mind that doesn't completely restrict us, because it doesn't mean that the solution isn't applicable to urban areas, but it was one of the key findings of the stage. And then another challenge we found was that due to time and resource restrictions in the discovery phase, we were only able to analyze at an LSOA level, whilst it would be preferable to be able to look at specific LV networks. And to do this, it would require a full geospatial analysis, including network asset location information. So if we move on to work package 3, which I think is going to be presented to you by Danny from Imperial College London on the next slide.
All right, thanks, Harry. Good afternoon, everyone. In work package 3, we aim to understand the technology's system implications and their benefits for reducing system costs and improving resilience. So we model the deployment of the REWIRE technologies to around 10% of domestic customers. The total REWIRE capacity is then for 15 gigawatt of combined electrolyzers with and fuel cell with 8 hours of hydrogen storage. We use the integrated whole energy system modeling developed by Imperial and used in several important studies for CCC, DNIM, and Carbon Trust and GBFlex study as analytical tool. The study was run on the 2050 net zero energy system background, with some days with extreme weather events where this energy demand is at peak while the renewable energy source output is low. So the results demonstrate that the REWIRE is actually offer an innovative solution to deliver a cost-effective, resilient energy system with net zero emission. And as Nick mentioned, that the gross system benefit of 15 gigawatt REWIRE is 2.95 billion pound per year, or equivalent with the 197 pound per kilowatt per year. So the main savings actually come from the capex reductions of low carbon generation, distribution costs, large-scale electrolyzers, hydrogen storage, and heating appliances, as this can be shown in the diagram on the right. The REWIRE also, we found that the REWIRE also improved the system flexibility and also supports more REST integration. However, we noticed that there are some challenges. For example, that we need to improve the efficiency of the domestic electrolyzers to reduce the increase in annual electricity demand because of the REWIRE technology. And a strong coordination between the electricity and hydrogen system planning and operation must also be established. So next slide, please. So in this slide, we show that the REWIRE can contribute to a 10 gigawatt reduction of distribution network capacity, shown by the left diagram, displacing 15 gigawatt of a mix of hydrogen CCGT and OCGT, demonstrated by the middle chart, and displacing gas and hydrogen by integrating renewable, as illustrated by the right diagram. So I hand it over back to Harry.
Here's Danny. So I'm back. If we go to the next slide. So work package 4 was somewhat of an extension of the technology feasibility assessment in work package 1. This actually extended on it by including commercial factors as well. So it included a steeple analysis of enable and barrier factors to widespread adoption, a roadmap from discovery to post-beta of the technological and commercial developments that will be required for widespread adoption to happen, and also a risk analysis, which included risk mitigations that could impact the future development of REWIRE technology. The main findings of this analysis basically boil down to the key features that require attention, those being as enablers, the maximizing of renewable generation nationwide, because obviously more renewable generation would lead to more of a demand for such technology. Improving component technology efficiency, again, as an enabler, because we believe there's a lot of improvement to be made in that space. And then finally, as a barrier to the solution, is consumer affordability of component technology. Some of the key risks that were flagged pre-mitigation were future variable tariff uncertainty, especially with if demand side response gets widely adopted, what will the variable tariff for the future look like, as well as just general cost of energy risk uncertainties in the future, 20, 30 years in the future. And then post mitigation, so the risks that are hardest to shake off would again be component costs. And so those, the questions of consumer affordability and component costs, they also tie into the question of whether the network would contribute some amount of money for such a solution if it is as beneficial as work package 3 has shown it to be. Finally, on the next slide, we can see where we're hoping to go for the alpha stage. Specifically, we want to formalize the requirements and design for such a system, especially, as mentioned before, the control system and the control logic. A more advanced analysis of commercial and technology would also be carried out. Again, questions of what policy changes need to happen to allow such a network investment in a property technology to happen, which obviously currently is unprecedented. Again, also in alpha would be the design of the prototype proposed for design in beta phase. And you can see also at the bottom there the list of the partners that we're hoping to have involved in our alpha submission. I believe if we go to the next slide, that's the end of our presentation. Yeah, so unless Nick wants to add something, I think we can go on to the Q&A.
No, all good, thanks.
Brilliant. Thank you so much, Nick, Harry and Danny. Really appreciate you giving your time and putting that presentation together. We've now got time for 5 or 6 minutes of Q&A. So we have got one in the chat. I would just like to encourage those of you who are participating in the webinar, please add your questions or clarification comments in the Q&A and I'll pick those up. So the first one is from Rob Walden. When do you predict that domestic scale electrolyzers and fuel cells will become available?
So I think it's sorry, Nick, you go ahead.
No, it's fine. You go, Harry.
Sure. I think the main restriction was in domestic scale electrolyzers. Fuel cells are largely readily available at the domestic scale because, as you might imagine, because they've been so widely adopted in the automotive industry already. So the fuel cells are quite easy to get a hold of at this TRL, but yeah, Nick, I'm not sure when we're predicting that electrolyzers or reversible fuel cells will be available at domestic scale.
No, and that's, to be honest, that's one of the key things that we need to take forwards into investigation is actually, are they likely to be ready at a domestic level, or is it actually more appropriate to find an alternative solution using larger scale, kind of centralized electrolyzers?
It's worth noting as well that our current scope for the alpha submission includes a hydrogen network connection. And so we're somewhat assuming that the electrolyzer would sit on the network now rather than in the property.
Thank you very much. Next question is from an anonymous attendee. Have you considered running a sensitivity analysis based on the Department of Energy Security and Net Zero AEM scenarios on future tariffs?
Yes, although frankly we didn't have time to do it within this phase, but it's one of the key actions for the alpha phase. Is to look at both what the current predictions are, but also to look at alternative options that aren't necessarily on the current list of ideas to see whether they'd be more beneficial to facilitate a system like this.
Thank you, Nick. The next question is from Duncan Bain. Is there an opportunity for district hydrogen, e.g. scaling this to a state scale rather than domestic, particularly for social housing, that might have many of the benefits of individual domestic installations, but address some of the challenges around scaling the hardware?
Yeah, again, so this project was specifically looking at behind the meter scale technology. And one of the reasons for that is the regulation preventing a energy distributor from owning energy generation or storage equipment. So we're effectively passing that ownership onto the homeowner. One of the key things that we discovered quite early on is that effectively this technology is not feasible for a flat. It would work for the block of flats, but it wouldn't work for the individual flats. So that's absolutely something we need to take forward as a consideration. And similarly for kind of new developments of housing, that kind of thing, you could fit potentially a more centralized system for the entire development.
Thanks, Nick. We have 4 more minutes for questions. How will the electrolyzer or fuel cell capital cost might compare to existing heat pump technology?
Harry, do you want to pick that one up?
Yeah, so I mean, in our CBA, obviously we modelled various technology costs. I'm just pulling up the actual CBA, see if I can spot it. So I think we're looking at the fuel cell varying somewhere between 10 and 15,000, whilst I'm afraid the heat pump isn't on the CBA here that I'm seeing.
Yeah, I think in summary, the heat pump was slightly cheaper, but not vastly. So they were a sort of similar magnitude of cost.
Well, thank you. We're out of Q&As on the in the box. However, I had one just out of curiosity. How are you sort of, as we move into alpha, how are you identifying suitable consumers to trial some of this technology? Who would be best placed to test it, to get really accurate data?
So I think it's something we're still discussing and debating, to be honest. There are obvious candidate properties that I think Harry mentioned around work package 2, where if you've got a rural residential property that has a gas connection that could be converted to a hydrogen connection, that is an obvious candidate sort of type of property. But at the same time, they're actually relatively few in number across the country. But that's actually not the point of this. The point of this is to enable improved resilience and improved decarbonisation. So actually, any property that has sufficient space to have the equipment installed would benefit from it, regardless of geographical location.
That's really, really great to know. Thank you, Nick, Harry, and Danny. Oh, we've had one more. We just have 2 minutes to get to it. From a resilience perspective, beyond operations, how does it compare to BAU solutions when relying on new tech that has scarce resources and water requirements? That's a bit of a chunky one for you there.
Sorry, can you just repeat that?
Sorry, that was very fast. From a resilience perspective, how does it compare to business as usual solutions? Thinking about the resources and the water requirements needed for this project.
Okay, so I'm assuming by business as usual solutions, it's inferring solar power with maybe battery storage, that kind of thing. One of the key goals of this project was to look at whether, if a property had solar panels and they generate excess solar power in the summer, they could effectively convert that to hydrogen for storage for their own use in the winter when there's not so much solar power. And it absolutely would achieve that. The challenge is actually a reasonable size of storage. In terms of the water demand, there is a small increase in the demand that you'd need for water, but when we looked at it, it wasn't like multi times the current usage. It was a relatively small percentage higher. We do need to do a bit more analysis into that in the next phase, in terms of if a large percentage of the residences did that, what impact would that have on the water network? But it doesn't intrinsically look like it's going to be a blocker.
Great, thank you, Nick. I'm afraid that's all we have time for. There is one more question in the Q&A box. I would just invite the speakers to address that in the box. If you could type an answer, and we will move on to the next project, please. Thank you very much for presenting. Okay, I'd like to invite the Wellness Project, Whole Energy System Resilience Vulnerability Assessment Project, which is led by National Grid Electricity Transmission, to present next, please.
Okay, thanks, Beth. Maybe if you can, yes. So, I don't know, am I audible, Beth?
Yes, we can hear you just fine.
Okay, that's fine. Thank you. So, thank you, UKRI, for inviting us to present our exciting and revealing project. And as you have said, it's Whole Energy System Resilience Vulnerability Assessment, with a resounding acronym, the Wellness. And you can see the collaborators, the leading collaborators that we are working with. Maybe next slide. So what is really it about our project? So our project, the problem statement there, we aim to tackle a key challenge to develop low carbon, cost efficient and resilient future energy system. But at the moment, the problem is we don't have, or there is no standardized approach to consider energy system resilience in decision making. We are aware of the need for resilience, for network resilience. Hence, we logged on to this strategic innovation fund call. And the major questions, the challenge areas, the challenging tasks that we are faced with are: how do we consistently evaluate and manage resilience? How do we capture the dynamic needs and changes associated with energy transition and climate change? And how do we also ensure an industry-wide decision-making across the distribution network operators and transmission operators, who are in this case the initial primary users of this project? And how does that support the net zero transition and create a resilient network? So that's what that slide is talking about. Maybe next slide. So to address this challenge, the project aims to develop a framework that can constantly evolve with the changing energy system to embed resilience in decision making. For this purpose, as you can see from the slide, the wellness partners, of course, NGET brings to the fore knowledge of the vast network, Great Britain's transmission network. The other partner, Electricity Northwest, operates a distribution network which is integrating an increasing volume of low carbon technologies, LCTs. We also have ARUP with different quantitative and qualitative aspects of resilience in industry. University of Manchester lead in detailed network investment and operational modeling. University of Cyprus accredited to advances in power systems, resilience and extreme events. And last but not least, Imperial College London, ICL, are bringing the use of demand flexibility across the networks, especially the distribution network, to improve resilience. Next slide. So, wellness, our project is being delivered really through 3 core activities. There are 4 work packages. The first work package is really a project management work package, which I will not spend time on, but these 3 are the 3 core activities. So starting with the middle rectangle, like the rectangle in the middle, is really the core of the project, linking the top and the bottom blocks there. And it talks to us assessing our understanding of what extreme scenarios are and what the stress conditions are. And also the aspect of how they evolve during the transition. Connecting to the top, we also have how we are reviewing, or how we have reviewed the existing resilience measures proposed by industry and academia, especially in this case, the role of demand side flexibility emerging at distribution level. Then at the bottom, the explore cost benefit analysis talks to the exploration of the costs and benefits associated with resilience based on formal cost benefit studies. We are aware of other related SIF projects that are going on, whom we have engaged and confirmed differentiation of scopes. We also aim to continue coordinating and align our approaches to network resilience and gather greater benefits to the energy system. That's what this slide is talking to. The next slide, please. So let me introduce you to Alex Eduardo Martinez to take us through the next bullet. Thank you.
Yeah, thank you, Dinesh. As Dinesh mentioned, one of the key aspects of this project is to bring resilience in a consistent way into decision making, and hopefully this can be used to inform regulation. Now, the concepts of resilience, the definitions have been changing drastically over the last few years. There is no single definition, and that's what is making this this particular type of work so challenging. Based on the feedback that we have received from different stakeholders or experience over the last decade or so, the conclusion is that we cannot have a single framework that is going to capture all the aspects of resilience. Instead, we need a framework that is a bit more flexible, that is capable of evolving based on our understanding of what resilience actually means. That said, there are some specific aspects, some characteristics that we have identified as critical for resilience in networks. Especially, we were focusing a lot on the ones that are consistent with the current view in the UK, and also those features that would allow us to capture or to evolve the type of framework based on how the market, how the energy system is changing. So some of these key considerations are, for example, the identification of what the extreme events actually are. So we need, or we have developed a framework that can consider existing risks, let's say taken directly from the UK's risk register, but also that can be extended to defining what risks actually mean for the system. That is, if you have an extreme event, depending on how it connects to the network, how it goes through the network, which parts of your system are more vulnerable. So rather than going from a specific risks to identifying how that risk, let's say that hazard, materialize in specific vulnerabilities of the network using stochastic approaches or other most advanced techniques. But the whole idea is that the framework has to give us the flexibility to go in this direction, because perhaps the risk register doesn't allow for stochastic approaches yet. But if we want to capture vulnerabilities and we want to follow the latest innovations from literature, we might be going in that direction. Other important aspects are the different phases of the extreme events, of the disturbances. unlike other type of topics, resilience considers that the system can fail, the system has to ride through the contingency, and the system has to restore, go back to the normal conditions. And these different aspects are critical for resilience. We might allow the system to fail or to be disconnected to protect it if we can restore it quite rapidly, or we can do some type of trade-offs depending on the specific needs of the system. We can customize our view of resilience based on the conditions of the system. But that also means that we need to regulate different aspects of the response of the system, going from investing in resilience measures, barriers, hardening assets, what's happening during operation, the impacts, and restoration. So all these different aspects also have to be captured within the framework. Moving on to other aspects, how the loads are changing. You can make a distinction between normal and critical loads. Some specific part of the network need to be able to maintain the supply of electricity more critically than others. But also now we have flexible resources that might not be as critical from the perspective of if they're disconnected, they affect customers. But if we keep them online, they might be able to support the rest of the system. They would be able to allow us to reconnect other customers. So these aspects have to be captured. And that links to this evolving understanding of what resilience is, but also the customization of the framework based on what is happening to our system. This is something that my colleagues from Imperial will elaborate a bit more. But as we decarbonize the energy system, we have more low carbon technologies. We have more intermittent resources, which are stressing the system, but also are giving us new ways to provide services to the system. So we need to capture those effects. And lastly, at the end of the day, we are focusing on the network. So we need to be able to properly model those networks. So it's not enough to just model how an event could impact the system statically. We need to know how that event evolves throughout the system. So potentially cascading effects, potentially interconnections between the different networks. If we go to the next slide, if we can transition to it.
We've only got a couple minutes left on this presentation, if that's all right, Alex.
Okay, so I'll go quickly then. So the specific framework that we have developed captures different aspects, going from the geographical characteristics of the network, the evolution of the event, basically what I was mentioning before. This type of framework right now is a work in progress. We currently focus on windstorms, on static characteristics, but what we want to do in Alpha is to extend this framework to also capture flexibility, detailed response of the network, and especially these interconnections between transmission and distribution. And this is something that now my colleague Dawe is going to be explaining in more detail, these interactions, this contribution of flexibility. So Dawe, if you want to continue.
Yeah, hi, thanks, Andrew. Hi, this is David from Imperial College. And in this project, so we would like to work on the demand side of flexibility to support resilience enhancement. So first of all, we would like to show how demand flexibility, especially the multi-energy microgrid, can be used to enhance resilience of energy supply. So in this project, so we try to model the multi-energy microgrid for multiple sectors, including electricity, heat, cooling, and transportation. So we would also like to model different kind of flexible resources, such as the backup generator, mobile resources, EV, and some other multi-energy resources. So our objective in this project try to evaluate the value of this local flexibility in providing resilience enhancement. Next slide, please. Yeah. In this project, we try to use different strategies of local flexibility to provide resilience. The first one is investigate the coordination effect over network and microgrid to provide the resilience. It can be seen from the bottom figure that microgrid 1 and 3 together supply energy to the middle microgrid 2 when there are several outages. And all the essential load can be fully supplied by the network and microgrid coordination. The second one is investigate the mobility and the flexibility of repair crews to provide the microgrid resilience. We also have a case of 3 repair crews that can route and dispatch in a multi-energy network. This repair crews can successfully repair the damaged lines and recover the network back to the normal operation. Okay, let's move to the next presenter.
Good afternoon, everyone, and thanks, Dawie and my colleagues before. I think the key point here is expected benefits from having resilient standards. I think at the moment, our counterfactuals are a do nothing scenario where we currently don't really have a commonly accepted resilience framework. However, we do have National Infrastructure Commission has recommended a resilience framework, and during the engagement with National Grid, electricity transmission, and other colleagues during discovery phase, we recognize that in order to propose resilience standards or embed that into decision-making process, we need to look at resilience from the different phases. So at the moment, I think we probably have FAS, NOAA, DFAS that's currently in the anticipate stage, but however, they do not really incorporate physical climate risks to quantify their impact on asset performance. Then we would probably need, as my colleague Alex touched on, fragility curves and different vulnerability models to identify how they may affect asset performance during different physical climate risks. And moving on, we currently have different grid code, distribution codes, the SQSS P28, where we set out the criteria and methodologies for planning and operating the electricity system. However, those codes are very deterministic, preventative driven, and only considers, again, limited threats that may not really reflect the shocks and the stresses in the future. So we kind of discovered in discovery phase that new metrics and regular updates need to be reflected, and as Alex also mentioned before, those metrics need to be adaptive to the changing focus and needs of the consumers. And we also have electricity system in the recovery stage. Electricity system restoration standards obligate the electric system to have sufficient capability and arrangement in place to facilitate a target restoration. However, we do not have specific metrics or benchmarks that can be applied to actually fairly and transparently evaluate different resources, their contribution to restoration and the recovery. So that is a key gap as well in the recovery phase. I think at the end is, in order to really drive adaptation and the transformation of systems, we need to properly value resilience, and as kind of recognized in discovery phase is building a business case or building the cost benefit analysis for resilience is challenging, is difficult, and we need to agree, and hopefully through wellness to can propose a common language to discuss how the changing landscape may affect the levels of resilience and how the different benefits of different mitigation and response strategies can be properly assessed. Word is also through wellness, we'll try to help the regulators to with evidence to value resilience in their decisions to support networks investment. Next slide, please. As an attempt to kind of bring out the benefits of resilience, we used some of the simulations we previously done in collaboration innovation project with NGET as well, the forward resilience measures project. And we have there first discovered that if we look at specific NOAA options, and we didn't really see much resilience improvement or contributions via the simulations of windstorms. This is kind of evident because the NOAA options at the moment are not specifically resilience driven, or they are not resilience orientated assessment approach. Whereas if we look at actual resilience measures, we can result in reduction in interruptions, varying from 34% to almost 99%, by 5% to 20% increase in asset robustness. Or if we employ the flexibility measures that discussed by my colleague Da Wei in terms of reductions in recovery time, we can also see a reduction in interruptions by 7% to 21%. So this kind of first addresses that in a way the hardening of asset provides much more significant improvement in resilience. But however, depending on the actual needs of the consumer, so whether that justifies is the associated or probably with less front capital expenditure, the reduction in recovery times via flexibility from the consumers may also satisfy the actual needs of the consumers. So overall, what we're looking at is wellness is trying to explore different measures and how they can be evaluated fairly, transparently, based on their actual contributions to resilience, and hopefully to help the network operators to justify their investment in different measures for resilience. With that, I'll hand back to Nash to look at next steps and conclusions.
Okay, thank you, Yutian. You really hit the ball running. Thank you. So next steps, the discovery phase is really highlighted the need to continue work, the need to keep going and refine our modeling, as well as build a demonstration of the dynamic system resilience framework itself, and also refine even our cost benefit analysis. We take cognizance that the output of this project will inform regulatory networks, and we really have to take advantage of the demand flexibility aspect, also link the modeling across the whole energy system, and just embrace all the demonstrable values that we have in terms of network investments, which enhance the resilience of the energy or electricity network. So I'm not so sure whether we are still doing good on time, but yeah, that's the conclusion of our project. And over to you, Beth.
Thank you so much, Tanash, and thank you for the whole wellness team for presenting. Unfortunately, we don't have time to do a live Q&A, but I'd like to invite the wellness team to answer the questions directly in the Q&A box. So if you did ask a question in there for the audience, then please keep an eye on that. They will answer it for you. Thank you all. I would like to invite the HyCoRe team to present their show and tell now.
Thank you, Beth. Good afternoon, everyone. My name's David Lynch. I'm a strategy manager at Northern Gas Networks, and I'm going to start by giving you the high-level context for our HyCoRe program before handing over to each of the work package leads to provide some of the headline findings from our project. Next slide, please. So our program was made up of 3 core partners, Northern Gas Networks, ORE Catapult, and Kineal Energy. And we also had a range of advisory industry partners, including UKPN from the electricity network. The core focus of our programme was to investigate key options and considerations for exporting offshore wind power, with a particular focus on the role of gas and electricity networks in transporting green hydrogen from offshore wind-powered electrolysis. In terms of outcomes, our programme was designed to gather new knowledge regarding the future energy system, preferred options around the optimal placement of electrolyzers and energy storage devices in order to inform, hopefully, the next alpha phase of our programme. Now, our alpha programme, my colleague Paul McKeever will talk a little bit around that a little bit later on, but just some high-level perspective aspirations we'd like to cover in that round will be around establishment of a test facility designed for validating software tools and models, proving out the component technology performance required for future energy system modes of operation as well. We're also going to be conducting in our alpha phase a review of gas network regulations and changes required to accommodate industrial scale hydrogen from offshore wind. So we've got 6 work packages. Next slide, please. What I'd like to do now is just give you an overview of some of the 4 technical work packages. So work package 2, we focused in on investigating the options for exporting offshore wind power. Here we looked at the best offshore electrolyzer configurations. We also looked at the value of storing energy in the pipeline, and we looked at what hydrogen technologies and test and demonstration facilities will the sector need going forward. So a bit of future gazing on that one. Work package 3 was the energy carrier medium. Here we used our partner Kinney-Wells clock software to broadly represent and simulate a gas pipeline into a REWIRE system, and what improvements could be made to the overall offshore wind farm design, and use that to make a comparison of electrical versus hydrogen systems for export. In work package 4, we also integrated analysis cost drivers. We looked at combining the outputs of work package 2 and work package 3 and looked at the main cost drivers of electrical versus hydrogen offshore wind systems. Finally, in work package 5, the impact on gas and electricity systems. Was there an opportunity there to reduce energy network investments through strategic deployment of electrolyzers, and what are the possible locations? And here we focused regionally in an area in Teesside, but in our alpha program, we'd like to open that up to a national level. We also looked at what are the best ways of using electrolysis and energy storage at scale in order to reduce network infrastructure costs. So I'd now like to just hand over to James Withers from RE Catapult to provide some of the headline findings from work package 2. James, over to you.
Thank you. Next slide, please. So on that first point about optimal electrolyzer configuration, we see that onshore electrolysis is currently easier, but offshore options have advantages around costs, time to deployment, and permitting, depending on the site and capacity. Overall, though, there was a broad consensus that the cost of hydrogen produced from offshore wind could be about £5 to £10 per kilogram today, but that could fall to £1.50 or £3 per kilogram in the coming decades. Next, we looked at changes to wind farm design, and although we didn't see that hydrogen would enable many changes to the wind farm design itself, we did see that it would be promising for allowing sites that are further from shore and in deeper waters to be developed. So we mapped that out as a function of water depth and distance from shore. So kind of near shore, shallow water, electricity is a clear favorite. As we get deeper and further from shore, there's a kind of tipping point. And then for those further from shore and deeper water distances and depths, we think that hydrogen is promising. If we move to the next slide, please. So the third thing we did was a case study with a simple analysis looking at a 100-kilometer long pipeline with a 12-inch diameter. And just based on the pressure difference in the operating range, we found that it could store over 400 megawatt hours of energy through line packing. And on a windy day, this would increase the revenue from a 900 megawatt wind farm by about 1.5%, equivalent to about £11,000 over the 24 hours that we looked at. Next up, we considered the economics of energy transport for pipelines, electrical cables, and hydrogen shipping. They all have their own niche. So ships are best for long distances, pipelines are most effective in high capacity middle distances, as defined on the slide, and cables are the most competitive in shorter distances. And the last slide, please, for work package 2, we had a look at the new engineering challenges that could benefit from new test facilities. So one of those is how to manage a wind turbine electrolyzer microgrid. And we think we can help advance that question by connecting electrolyzers to grid emulators to enable sophisticated electrical testing, or even to a real wind turbine. And another example was that we saw for subsea systems as a question around how can we confirm that current or repurposed pipelines are suitable for hydrogen transmission. So we think there's potential for establishing a submerged hydrogen pipeline test facility. And that's all from work pack 2. Thank you.
Thank you, James. Next up, we have Hamza Sajid, and Hamza is from Kennywell Energy. Hamza.
Thanks, David. I'm delighted to present the outcomes of our study in this work package, which reveals some exciting possibilities for the future of renewable energy. The implementation of hydrogen inter-array systems offer significant advantages. Mainly, these systems require shorter pipe lengths compared to your traditional inter-array cable systems. But more specifically, we found that this can become cost competitive as we scale up offshore projects, highlighting the potential for hydrogen integration. Additionally, our research indicates that pipeline systems enable the substation position to be less sensitive to inter-array costs. Now, this provides more flexibility in the overall project design, and savings in other areas of the system can be achieved, such as reducing the length of the export cable. Moving on to the export system, we also examined the economic viability of hydrogen for a 1.2 gigawatt case study. And our findings demonstrated that projects situated further offshore present more favorable conditions for hydrogen integration. And in this particular case, we found this to be at distances of greater than 150 kilometers. Now, this is a significant milestone as it opens up opportunities for remote and deep sea wind farms to leverage the benefits of hydrogen integration. Next slide, please. So when it comes to the inter-array system, we've identified significant cost differences between pipes and your traditional cable systems. Overall, project costs with the use of pipes are considerably higher, and to achieve cost competitiveness, it's crucial to focus on cost reduction measures. So specifically, pipe purchase costs need to decrease to 30% of the current cost assumption. So by exploring alternative procurement strategies and leveraging economies of scale, we can really drive down these associated expenses. Similarly, pipe installation costs need to reduce to 20% of the current cost assumption. Now, in relation to the export system, we evaluated the CapEx associated with hydrogen and electrical options for offshore wind farms. And our study revealed that some hydrogen systems exhibit lower CapEx than these electrical systems for projects located more than 100 kilometers offshore. Now, again, as I previously mentioned, it's demonstrating that potential economic advantages as we, move further offshore, I guess. Now, to achieve a fair CapEx balance between both these systems, cost reductions are required. Specifically, in the case for a decentralized system, we found that the electrolyzer costs need to be reduced by around 25%. Similarly, pipeline purchase costs need to be decreased by about 75%. Now, this means exploring alternative materials and technological advancements to find these cost savings. Lastly, it's worth noting that substation platforms contribute to approximately 7 to 10% of the overall export system CapEx. So optimizing the design and deployment of these platforms can further enhance project economics. Back to you, David.
Excellent, Hamza. Thank you very much. Next up, we have John Nobu from RE Catapult. John, over to you.
Thanks, David. Next slide, please. So work package 5 was around answering the question around flexibility, and that focused on the impact on gas and electricity networks. So we set out to answer a number of questions. The first question really was around finding a potential location for a future case study in the alpha phase as well. In this, we reviewed the long-term development statements for both the gas and network operators and electricity network operators. And as you can see in the diagrams there, we saw that there is a potential for network congestion relief by using electrolyzers. In this, we saw that from my initial analysis, Teesside was a good region to focus on. That's based on the fact that 90% of the homes are already connected to a gas network. The existence of pipelines and infrastructure plan with Project Union, East Coast Hydrogen, and even in the North Sea with the North Sea cross-border hydrogen pipeline 1 and 2 as well. One thing we highlighted here, we really wanted to understand a little bit more was around the water requirements for a sample in the Teesside region, if we were to go on this with a further case study as well. The second question there really was more about how do you actually introduce these technologies from hydrogen at scale? And we sort of tried to focus on how that relates to costs as well. And that showed us that actually the electricity market structures and also the market and the existing electricity market design is a key factor in that needs to be sort of understood better in terms of understanding how hydrogen could form a reliable sort of participant in existing sort of way markets are run. So the questions there really was understanding that wholesale electricity prices are a main factor, and in order to sort of tackle this would be understanding how the new sort of hydrogen strategies for markets would work. And we're really interested in exploring a further cost benefit analysis in the next phase around understanding if there's an actual potential network we could service, which can identify that could actually be useful to actually prove the viability of hydrogen in the network as well. Next slide, please. The third question really now was we've finished with all the aspects around the networks, but we wanted to focus on offshore wind generation, understanding the potential for hydrogen production from that. So with the same sort of idea that we have identified Teesside as a region, we set out to understand a little bit more how sort of Teesside, the region is in terms of proximity to existing offshore wind farm sites and how the potentially could be used for hydrogen production. So in there as well, we identified that already there are existing wind farms there with capacities above what maybe might be possible to connect to the grid in the future. And there is a potential that some of that capacity could be used for hydrogen production as well. One thing we really wanted to understand was how this would really integrate into the network. And we understood that there's actually existing gas pipelines in the North Sea that can be repurposed and by blending hydrogen in as well. And this is one of the areas we're really interested in exploring further in the next alpha phase case study. The fourth question now was really around these technologies are going to be integrated into the networks, both electricity and gas. Would they actually meet the existing testing and validation requirements to perform if they are to be operated within the network as well? So we looked at two areas. One is grid compliance, which we realized that there isn't so much awareness on how much hydrogen systems, be it electrolyzers and fuel cells, will be connected. And we did see that possibly most of those systems can actually comply, but there's still a bit more understanding into how that would actually happen in terms of the existing policies and regulations regarding that. And the second aspect really was around actually participating in the existing markets. So how actually would you trade hydrogen? And we realized that hydrogen as a technology could actually participate in the existing market services provided by National Grid. But we did see there that there's opportunity there for actually a closer sort of deeper sort of design that will integrate the technologies much better in a similar case of how initially battery energy storage was introduced into the market as well. And I'll hand over back to you, David.
Thanks, Paul. Sorry, thanks, John. And next up, finally from the HyCoRe team, we have Paul McKeever from ORE Catapult.
Okay, thanks, David. So yeah, looking forward beyond discovery phase and what we do next. So opportunities identified. So certainly continued engagement with the advisory board, which has been really valuable so far. And there's also an opportunity to widen that project engagement. And then looking at the work package outcomes themselves. So work package 2, we've already identified the benefits of test infrastructure. 3 and 4 has showed us the value of developing analysis tools. And work package 5, the need for deeper cost benefit analysis for network investments and infrastructure upgrades. And then in terms of the potential benefits of those activities, so that engagement, that stakeholder engagement will help us to improve our knowledge and also avoid duplication from similar projects. The test infrastructure, two reasons really. Firstly, validating our models and also de-risking the key component technologies. And finally, those analysis tools, we can strategically use those to greatly assist our future energy system design and optimization. So next slide, please. In terms of project thinking evolution, one of the big things that we've learned in the discovery phase is the value of a regulatory landscape analysis. So that needs to be in an alpha phase program. So thinking about the alpha phase program elements, we'd certainly want to do more technical, economic, regulatory and market framework analysis. We'd want to develop those tools that we've identified in discovery for managing systems at both regional and system level. work package 5, further cost benefit analysis, looking how far we can take hydrogen as a service with using initially the Teesside case study. And then finally, more focus on the energy generation aspect, particularly around the wind turbine electrolyzer systems, both from a technical, economic point of view, and also that test infrastructure. So if we can validate those tools, if we can de-risk that technology, then that provides that investor confidence before you really start to go into a big demonstration scale activity. So that's all from me. Thanks.
Thanks very much, Paul. That concludes our presentation from the HyCoRe team. Beth, back to you. Thank you.
Brilliant. Thanks all for a very, very thorough presentation. You have a lot of questions in the Q&A. We're not going to have time to get through all, but I'll try and pick off a few. So how does building the test facility differ from core BAU activities for the catapult? And have you identified any overlap between programs like the Hydrogen Innovation Initiative?
Shall I jump in there, Paul?
Yeah, you can have a go, James. I'm happy to supplement. Yeah.
Yeah, super. So in terms of new aspects around these test facilities, so a big kind of trend that we're seeing is this importance of hydrogen to offshore renewables, and so this is we're pleased to kind of be in the commissioning stages of a small scale system at Blythe that's going to use hydrogen, and that's the first time that we've had hydrogen equipment on site, and so although we're kind of used to working with flammable gases and high pressure gases, the fact that it's hydrogen is still breaking a lot of new ground. So we're covering a lot of safety aspects there, and that's helping us. And once it's up and running, even more so, that's going to help us to tap into electrochemistry in a way that the organization has never done before, and thinking about kind of pressurized gases for energy storage in a way that we haven't done before. And so we're really excited for that. So the Offshore Renewable Energy Catapult is in the Hydrogen Innovation Initiative, and this is we're really pleased that this kind of work is interesting for a number of different funding organizations, and so there is some overlap there. I think in HyCoRe, we're especially thinking about that kind of cost reduction and then kind of strategic placement of electrolyzers as well. Thanks.
Thanks.
Yeah, just to supplement that, one of the key things about the HySeed program is it's a seed program, so it doesn't actually do any physical hardware demonstration or test rig development. It's kind of the precursor for that. So there's an opportunity to use the alpha and beta phase programs to really accelerate and get the boosters under that and get maximum benefit from the learnings of HySeed.
Thanks, Paul. Thanks, James. Next question. Has your study found it more commercially attractive for wind farms to produce and export hydrogen rather than power? What key assumptions in your modelling have high and low confidence?
We did a bit in that, but Henna, you go first, if you'd like to.
Thanks, James. I thought I'd just jump in there. So I think what we found is that hydrogen was commercially more attractive in certain situations, and as Hamza said there, it's in particularly far from shore projects that we found it to be most attractive. Your point there about assumptions is an excellent one, and perhaps I can't really go into so much detail on this call today, but what I would say is that the work of Work Package 4, where we were looking at the cost drivers and exploring the impact of those assumptions, was where we tried to address that there, and really looking at how much do we need to bring down the cost of the assets that we've got to make them cost competitive with the electrical system. I don't know if you want to add anything there, James or Hamza.
I guess over to you, James, if you want to input anything.
Hamza. Yeah, I think that point about assumptions. So there's so many different dimensions. So just to name like 3 is the distance from shore, the water depth, and the capacity of the wind farm. And there's a whole bunch more besides that. So it's easily like a 7 or a 8-dimensional type of problem, and like mapping that out between different studies. And some of the studies will show loads of information, and some of the studies are more consultancy style, so they won't be as much information upfront. So it's not quite as clear like how to compare them. So I think that's something that we're really looking to drill into in an alpha phase. And I think another thing is there's so many different possible business models as well. So it's very easy to come up with a business model that makes hydrogen look terrible. That's easy to do, but there are options where it is possible to kind of bring it down so that it looks favorable. Yeah, and for example, like taking account of the value of the energy stored in a pipeline, that's lost in a levelized cost calculation, but that would be captured in other economic metrics like net present value and payback period. Thank you.
Great. Thanks all. I'm going to stop there for questions just because we're due to have a break. We're going to have a 10-minute break now and due to be back to resume the show and tells at 3:25, please. And we'll kick off just after 3:25. Give it a minute or two to allow people to slowly come back in after the break. And then we will shortly kick off with the NextGen Electrolysis team. I'd just like to point out some of the previous projects have provided some really detailed responses to the questions that were put into the Q&A, which we didn't have time to do live. So if you did put a question in there, have a flick through the answered questions in the Q&A box. There's some really insightful stuff in there. Okie dokie. I would like to invite Charlie Newbold to present the project NextGen Electrolysis, Wastewater to Green Hydrogen for their 15-minute show and tell.
Thanks, Beth. So we have next slide, please. Lovely stuff. So hi, everybody. My name's Charlie Newbold. I've been project manager for HydroStar for this discovery phase, and I'll be taking you through our project NextGen Electrolysis, Wastewater to Green Hydrogen. Next slide, please. So the challenge we've been focusing on is obviously challenge 3 to improve energy system resilience and robustness. Now, Wales and West and other gas networks nationally are investing heavily in preparing the network for large quantities of green hydrogen being injected and understanding the effects hydrogen will have on the network. But at present, green hydrogen production is limited by operational constraints and infrastructure requirements. I'll come on to these more later, but two of the key considerations are where do we get the electricity from and how do we obviously supply enough water for large-scale hydrogen production. Now, the reliance on the electrical grid and mains water infrastructure is limiting the locations that green hydrogen can be produced, and therefore the resilience of gas network supply and the ability to control where hydrogen is flowing within the grid network. This is also affecting the costs of production through requirements for compression and transportation. So next slide, please. Our project really is seeking to address these issues and others, with our objective being to lower the operational barriers of green hydrogen production by using water that is less pure, addressing real-world manufacturing and operational constraints, and reducing hydrogen production cost. We've placed particular emphasis on the water component of green hydrogen production. Now, current electrolyzers are using pure and ultra-pure water as feedstock, and this has a very high water demand, not just from the direct production of hydrogen, but also during the purification process. So to make 1 litre of purified water, there's actually at least 6 litres of water which is required. And this is posing threats to water supplies in specific areas across the country when hydrogen is scaled in line with government targets, particularly in areas where water shortages are a common occurrence over summer. So therefore, this project has investigated different levels of water purity, starting with tap water. This obviously isn't a waste source, but it's not an ultra pure source like the highly purified water. And then also using water like rain and storm overflow water from rivers. But just being able to use the wastewater isn't the only consideration from a lack of infrastructure perspective. So it's also to do with electricity availability. So we've been modeling matching electrolyzers to fluctuating renewable production, which combined with the water side of thing facilitates a more distributed approach to hydrogen production. And the benefits of a more distributed approach is really what is increasing the resiliency, how this project is looking to increase the resiliency of network operations. So being able to inject hydrogen into specific nodes along the network, it allows us to control hydrogen movement into specific lines, which are strategically beneficial for network operators, but crucially also reducing the cost for network users by removing compression and transportation. Next slide, please. So moving on to kind of some of the work undertaken, I'll start with what the water usage and the electrolyzer. So we looked in detail at rainwater in Exeter as the initial wastewater source, and the analysis of the rainwater really found that we see consistent ions in the rainwater, but that the concentrations of these vary. So you can see month to month there that obviously the concentrations of each of the different ions are going up and down. Now, this to kind of account for this, we developed the chemical equations to predict the potential byproducts from these different ions, and therefore, what the considerations for what we'd have to deal with by utilizing water that isn't super pure. So these really have guided the considerations for Alpha in terms of electrolyte composition and electrolyzer specs. So from an electrolyte perspective, the electrolyte is going to need to be changed slightly dependent on the concentration of ions present in each batch of water. What we'll start to look at is, how much do we need to change specific components within the electrolyzer to match to basically the batch of wastewater that's being used. And then from an electrolyzer perspective, what are the different materials that we can use for the electrodes to account for the different byproducts, and also the power levels that we can use within the electrolyzer to see how that will affect the different byproducts that are produced. Next slide, please. So we also wanted to look at the different components of the green hydrogen supply chain. Now, we mapped and modeled production, all the way from kind of generation of electricity, compression, water usage, etc., all the way through to use and consumption of the hydrogen. So doing this highlighted some key areas that are facing large demands that can be minimized to increase overall efficiency rather than just a single point efficiency, and therefore reducing the cost as much as possible. And two of these were obviously the compression and the transportation element, which using a distributed production strategy helps to reduce. Can we click on one, please? Thank you. So we also looked at the matching to fluctuating renewables and using a techno-economic model to predict the hydrogen outputs from the different sources, and also the cost that this would entail. So obviously the first one at the top there is the solar graph, and the second one below is the wind profile of matching to hydrogen production. So what's interesting about the solar one is when the water is most plentiful, i.e. in the summer, when the water is the least plentiful in summer, but the power is the highest available, that's what's going to make an issue for the water consumption if we're using highly purified. Whereas for the wind profile, it actually fits quite nicely as to when we're going to expect there to be more wastewater being produced. And what this also showed was to flatten out the capacity factor of the electrolyzer. Actually using a hybrid system of the two would be very beneficial. Next click, please. We then also took an initial analysis into gas network operations, primarily methods and locations for injection. So we looked at some high demand users that Hydrostar have been in contact, kind of working with for quite a while, and then mapped the network routes around these sites to identify potential injection points which would be beneficial to a network operator, but also deliver the required quantities of hydrogen to the off-taker. And identifying the key injection points also has a large resilience benefit, but I'll cover those further down. Next slide, please. So in terms of the potential benefits, now this is essentially looking at using just tap water without the need for purification. So not even looking at waste sources straight off the back. Now, we can save an estimated 4.5 Olympic swimming pools per gigawatt of electrolysis per day by just simply removing the need for highly purified water. So not even using a wastewater source yet, just removing the need for purification. And when you factor in the usage of wastewater still, it reduces it by basically another Olympic swimming pool daily of mains water. Next tab, please. And to put this in a scale which is actually kind of relatable to, that's 7.65 million kettles filled daily to achieve the same amount of water consumption. So it's an enormous amount. Next click, please. And also just another one, if you were to take a 10-minute shower each day, you could have 385 years worth of showers for just for 1 day's worth of purified water demand. Next slide, please. Thank you. Then also looking at the other side of it, which is not the water element, but the other elements of compression, for example. If we just remove the need for compression up to 300 bar across the course of a year, it's the same carbon saving as taking 17,600 cars off the road. So, a massive saving really in carbon. Next click, please. And that's also equivalent to over 400,000 standard UK homes equivalent electrical demand for the year. And then we also quantified this in terms of the cost of removing compression, removing the need for purification and the transportation of hydrogen. And we were seeing, between a 20 and 24% reduction in the cost of hydrogen across its lifespan. Next slide, please. So how's wastewater usage and mapping and modelling the different demands across the hydrogen supply chain relating to user needs? First and foremost, these strategies are, to reduce the cost of hydrogen, both from an initial capital expenditure and operational energy perspective. And this is obviously currently a key barrier to wide-scale hydrogen usage. Next click, please. We then have greater modulation of hydrogen flows across the network. Now, by generating hydrogen in a distributed manner without needing significant water or electrical infrastructure and injecting into specific nodes, tracking hydrogen movement is far easier for a network operator instead of it just going in one location and then being consumed somewhere downstream. And it also enables network quantities and pressures to be kind of reinforced, but more significantly, it reduces a single point of failure. So in the event that one hydrogen generation plant comes offline for a period of time, the other generators along the network are still operating and delivering hydrogen instead of, extremely large plants, which if they go offline have significant effects on network levels of hydrogen. Next click, please. And then the case of sensitive users with different needs. Now, some users will need high concentrations of hydrogen earlier than others, and by injecting into nodes along the network, we can deliver this without forcing current users who are constrained to higher purities of natural gas for a period of time because they've just bought new plant. So this basically, if it would cost them too much to immediately switch to, not immediately, but within the next 5 to 10 years, switch to hydrogen usage, we can still actually modulate the amount of hydrogen natural gas that they're going to receive. Next slide, please. So with this in mind, we are seeing a lot of opportunities being created from using less pure water and injecting in a distributed manner. So one of the things that we're going to start looking at in the alpha phase is actually using processed wastewater. So not just from rain or from kind of storm overflow, but actually, water from processes used on site. And, there's the potential for a bit of a co-location strategy there in terms of using their on-site wastewater and then turning it into energy for usage on site. We can also look at, reduce reliance on water supply, which enables a more guaranteed production. So particularly in areas which are facing water shortages, like I mentioned earlier, actually, if we can use the wastewater sources available, we're not constrained just to the mains water that's available. Now, distributed production at certain nodes of the gas network, this is, essentially to increase the resilience of the network. So how I talked about the reduction of a single point of failure and actually having lots of different generators to inject into different branches of the network and supplying the hydrogen exactly where it's needed at this point in time. And then also that results in lower costs from removing the need for any sort of transportation of hydrogen or compression to get it into the network, because we looked at different network line pressures, and actually the electrolyzer will output pressure that's higher than network levels anyway in the lower pressure lines. Next slide, please. So our thought evolution throughout discovery, it's really been guided by the feasibility studies confirming that using wastewater and other strategies can be very beneficial to hydrogen costs and resilience of production. Now, the key development really is focusing on co-location and a multi-focus strategy. So from customer perspectives, potentially utilizing processed wastewater to create their on-site energy requirements, and also, in certain cases, looking if we can utilize the oxygen on site as well. And then for networks, being able to inject at specific nodes to track more easily where the hydrogen is in the network. So therefore, with alpha focuses for next steps, what we're really going to look to do is start developing some actual kind of physical experiments. So first of all, well, I'll start with the electrolyzer. Actually, we're going to look to create a kind of 2 kilowatt unit, which we can start to do some tests on wastewater at a small scale, just to see, how it will react to utilizing different wastewaters. And then to match with that, we'll be modeling the electrolyte usage across the changing concentrations of ions that we're potentially going to be seeing, and also electrolyzer power levels. And we'll be working with the University of Exeter to do that for their kind of simulation and modeling ability, and also kind of access to facilities that they already have. Now, also we're going to start simulating the effects of injecting hydrogen into specific nodes on the network, and actually how this is going to affect customers, producers, the network operators in terms of hydrogen percentages, costs, and sensitive customer requirements. and then just really looking at, you know, more tailored solutions for sensitive customers who require hydrogen in higher concentrations. Next slide, please. Yeah, well, thanks for listening, everybody, and I'll take any questions now.
Thanks very much, Charlie. That was a great presentation. I'm going to kick off with the Q&A because we've only got a few minutes. So David Elam says, thank you for a really interesting presentation on wastewater. What assumptions did you use for modeling the rainwater gathering? For example, is it assumed that it's taken from existing drainage systems? And if so, are there any impacts on the wider water system that should be considered?
Yeah, so really that's a bit of a case by case basis, really. So some of the customers that we're working for already have systems which essentially, you know, are directing the rainwater into specific channels. You know, as you say, in terms of existing drainage systems, the effects, you know, the potential effects on the wider water system is definitely something that we want to look at. You know, because obviously, if they're normally discharging a certain amount of water into the system, we don't want to disrupt that. So we look to work with you know, the kind of the water operators in the area as well to see how that would affect it, and really with regards to that, you know, potentially using processed wastewater in the future, a lot of people have kind of licenses to discharge a certain amount at a time. So what we can do is actually use the excess that they might have over and above their discharge rate going forward. So it's a bit of a case by case answer, I'm afraid, but you know, it's certainly the effects on the wider water system is something that's really important for us to focus on.
Thanks, Charlie. Someone would like to know, is it possible that you could share a report on some of the data that you've gathered within standard engineering units? That would be really helpful to understand some of the outputs of the project.
Yeah, no, that's no problem. Just drop me an email and I can send over some stuff.
Fab. Tom Notman would like to know, how does the quality of the wastewater affect the hydrogen production and working life of the electrolyzer?
Yeah, so this is you know, going to be really a key focus for Alpha. So one of the things we want to know is how is it going to affect the efficiency of the electrolyzer, and this is going to really depend on what the wastewater is. So if there's certain ions in the wastewater, this is going to have more of an effect than others. So if we just take chlorine, for example, from, you know, using kind of a more brackish type water, there's a lot of considerations we've got to take there, because if you use the electrolysis at the wrong power level, you can create chlorine gas, which obviously we don't want to do. And obviously, you know, with every kind of byproduct that's created, the efficiency could be affected. So that's really what we're going to look at simulating in the next phase. And then also with regards to the lifespan of the electrolyzer, what we're going to do is look at different potential electrode materials that, you know, aren't so rare and basically rare and expensive, so that they could be, you know, it wouldn't be as much of an issue if they got degraded more quickly.
Thanks, Charlie. I'm afraid that's all we've got time for in terms of the live Q&A. I would like to invite you to just answer one more question from David Elam in the chat, if you don't mind, and we're going to move on to the next project. Thanks so much, Charlie.
Cheers.
Okie dokie. So our final project in the show and tell is distribution network information modeling. So I'd like to hand over to the DNIM team to present their Discovery Round 2 project.
Sounds good. Thank you, Beth, and thank you again for allowing us to present some of our thoughts on this project. My name is Mersim Rajamitovic. And everybody can hear me, okay? Just to confirm, right, before I get too into it.
Yeah, all good. I can hear you just fine.
Perfect. Today I'll be presenting on distribution network information modeling project, which we've collaborated with SGN on. And yeah, if we can go to the next slide, please. Next slide, please. Okay. So in August of 2021, the UK unveiled an aggressive strategic energy policy transition to a world-leading hydrogen-based economy. These policies set out to reach net zero by 2050. For gas utilities, this represented a powerful shift from methane to hydrogen-based energy ecosystems that have introduced a variety of questions regarding cost effectiveness, safety, and risk mitigation. So prior to that transition, gas utilities would be tasked with demonstrating the economic benefits of utilizing existing network infrastructure with hydrogen compared to laying new electrical-based heating infrastructure. And so, as you can imagine, really the kind of two core, questions here are, how can we use the existing gas network infrastructure, and what's the cost associated with doing so, and what are the safety risks to consumers, and how can we mitigate those risks before injecting hydrogen? So for the latter, we use the example of, as we begin to inject hydrogen, every consumer will need new appliances. And so if there are unknown parts of the network, how can we mitigate those risks and ensure that we're pumping hydrogen into the network, and knowing all the paths of the hydrogen within the network, so we can ensure that the consumers were adequately prepared to be safe when this hydrogen injection takes place. So, in the case of current gas utilities now, for example, for SGN, in the case of SGN, there are 74,000 kilometers of pipeline, and ensuring they're resilient and robust ahead of this transition is a really important feature of the transition to hydrogen, and ensuring that the 5.9 million current customers are able to safely take that hydrogen into their homes and be able to use it. Currently, there is no viable method for collecting this data on a time or cost basis. So, and if you could imagine mapping the whole network to ensure that all of the taps and joints and all of this huge amounts of metadata are considered as part of building this economic model, that would take a substantial amount of, in the case of push rod camera inspection and things like that. This would be highly disruptive to consumers and very costly to gas utilities. So to address this, we were proposing the development of a DNIM robot. DNIM is our distribution network information modeling system. And this is a robot that is an autonomous tetherless robot that we're proposing to deploy into the live gas mains to map the network from inside the network, thus allowing gas utilities to perform this mapping without the disruption, without the substantial cost to consumers. All right, if we go to the next slide, please. So current gas pipe records are just an amalgamation, really, of analog information from the time that they were laid down. So in the case of gas in the past in the UK, for example, could be upwards from 1880 onwards. So there are new mapping initiatives, as in the case of London, where we're beginning to digitize these network. In the case of London's underground, digital initiatives. And in this case, they offer a lot of opportunities for us to close gaps on some new pieces of information. So as you can imagine, some of the current data to date may kind of share kind of what the size pipe is, what material is. But there could be, there are gaps associated with what are the joints, what are the taps. And as we kind of shift back to the economic assessment model, gas utilities will be tasked with kind of understanding what is the cost to repair and remediate their network ahead of these, the hydrogen injection, and what is kind of suitable and what is not suitable. Are there any high risk features? What is the cost of repair and or remediation of those features? So this is kind of what we would call here is now building this business information modeling or building information modeling. So some people may know the acronym BIM. And so, this project marks a vital step to strengthen the UK gas network's robustness and enable this transition, and ensure the safety to the end consumers. We go to the next slide, please. So, as I mentioned, really the goal is how can we collect this data and how can we kind of close the gaps on some of the kind of really critical pieces of data as we digitize the network. So in the case of some of these, higher risk features, joints, taps, plugs, any unknown parts of the network, how can we collect that data and how can we stream that into some sort of GIS system that has, these BIM level outputs? And, obviously it's alignment to some of the ongoing digital initiatives in London and across the UK as well. But really kind of using this is also an opportunity to that could in the future be deployed to other pipe networks. But as we kind of discuss this with respect to making, ensuring the resilience and robustness of the gas networks, ahead of the transition, it can also potentially be used as a tool for ongoing construction and maintenance as we kind of move past the hydrogen injection point. So really kind of powerful problem for us to solve with this kind of autonomous tetherless robot. So if we go on to the next slide, please. So that kind of brings us to our current project. We're delivering this discovery phase. Previously, ULC and SGN have completed early stage R&D projects where the conceptual pipe mapping method was investigated and has been defined as DNIM. Again, DNIM is a proposed tetherless robotic system that can perform the network mapping from inside the pipe. When combining this advanced mapping techniques in conjunction with machine learning-based feature detection, gas utilities may identify and quantify the cost of repair and remediation of these high-risk features in their network. Meaning that as the robot is beginning to scan, we can not only have the robot effectively know where it is, but also identify where these features are in respect to the network and be able to kind of attribute some cost of repair accordingly. So these outputs have the potential to allow us to digitize the network through kind of these, again, building information style models, where we're having these 3D models with these machine learning based feature detection and categorization. So this work in the discovery phase focused on the business engagement on SGN side through their organization about where can this technology offer benefit, and so that they've kind of reiterated their commitment to continue and pursue this and move forward with the DNIM project. As far as the alpha phase, kind of our focus here was preparing this roadmap for development through alpha and beta phases, and showcasing some of the works that we've previously done. And as part of this project, this was a no cost submission from SGN and ULC to kind of show that commitment through to SIF. So if we now kind of get into the next slide where we can kind of start discussing some of the more technical aspects. So ULC Technologies has over 20 years of experience of developing these robotic solutions and deploying them in live natural gas environments, and we really do so by really two teams, one of which is our R&D team, one of which I work on, and the second of which is our field services team. So during this 20 years, we've developed a significant amount of expertise in machine learning and computer vision, which are really core capabilities and core skill sets needed to drive this project. And so in this case, we're looking at just some examples of the AI and machine learning models that we've developed in the past. So in this case, this is a live gas main, and this is kind of just some of the first instances of the first cog that would kind of drive home this project. So being able to process some of the video footage from a robot inside a gas main and identify, in this case, some examples of joints and taps in the environment, in which in previous cases where a person would have to kind of sit there on a truck in a cordoned off part on the road and sit there and review that footage for 4 hours or however long it would normally take. So this proposed technology for DNIM is comprised again of these two core features: the accurate localization, and secondly, the use of machine learning to identify these features of interest. So this is just again an example of some work that previously ULC has developed, and kind of one of the core technologies to be used here. And so if we get into the next slide, please. So again, DNIM is the distribution network information modeling. So DNIM is a multi-robot system whereby two robots are collaboratively mapping infrastructure. This proposed approach is done by having these advanced localization capabilities, as well as the use of machine learning to categorize these pipe features. The proposed robot is tetherless and autonomous, and can travel into the network to collect data, thereby kind of reducing the overall or potential overall number of excavations required to perform this assessment. So DNIM offers a safe, accurate, and cost-effective asset surveying solution that will help Great Britain's gas networks undertake a full economic assessment of their networks whilst maintaining the supply or the security of supply. You know, as I mentioned, this can be, you know, potentially done in live gas. The results of these mappings have the potential to provide the knowledge-based information required to undertake large pre-construction works on natural gas infrastructure ahead of the conversion to hydrogen. So, for example, you know, what plugs and what fittings need to be replaced. Essentially, you know, what sections of the network are metallic, what joints need to be remediated, et cetera. And so this project will also generate key learnings around the latest 3D mapping technology and machine learning for use in mapping and other applications. So in addition to kind of the greater level accuracy existing networks, along with the correlation to above ground infrastructure, this result, you know, provides SGN's design and planning teams the potential to design gas mains replacements projects with the least amount of excavations required, or the greater use of keyhole technology. So this would greatly improve the customer disruption and increase the efficiency of planned works. Moreover, repair teams could also utilize this mapping platform to identify features in the range of reported gas escapes, blockages, et cetera, and resulting in a kind of a low-cost solution that could increase the use of keyhole technology and decrease the size of traditional excavations. We go on to the next slide, please. So in this case, now we're looking at in the case of the in the case of the collaborative robot, we're looking at the face of the projected light or projected laser. In this case, we're using this mathematical algorithm to track the position of these lasers and providing very accurate localization. This generates a 3D point cloud. So this figure on the right side you see is, in this case, is still 2D image, but it would be what would be a 3D point cloud. And so you can turn it and see that, you know, generally speaking, that it could potentially be 3D in nature. If we go on to the next slide. So that was really the first cog is that accurate localization. The second cog is now once the robot is effectively localizing in the gas network, how can it collect data for these features of interest that have historically not been captured on traditional drawings and such. And so in this case, we have a secondary camera system that can you know, take these high resolution videos and be later processed in machine learning to identify, in this case, joints, taps, or potentially other high risk items. And so really when we have these two you know, data sets taking place, we can have this process take place with limited or with significantly reduced disruption to consumers. Making this a tetherless system allows the system to navigate deeper into the network and thereby reducing, again, the overall potential number of excavations to make this assessment. We shift into the final slide. So DNIM will deliver value directly to the gas networks by reducing theft of gas, as well as decreasing the cost for customer connections. Furthermore, DNIM will offer future savings to consumers by enabling superior energy models. This will reduce the spend on upgrading the network for future energy scenarios and ensuring the robustness and resilience of the energy system. Having this fully digital record of the network could also allow customer inquiries for new connections or alterations to be delivered through the use of smart engineering and commercial models, thereby reducing SGN's cost to serve and other gas networks' cost to serve, creating savings for the consumer. So kind of as far as our next steps, we're looking to kind of progress and prepare a proposal for the alpha stages for validation testing and some updated conceptual models of the system. So Beth, that was kind of all I had on my end. If we can kind of shift into the questions, I think we're right at time.
Brilliant. Thank you so much. Actually, my background is kind of robotics and stuff as well. So that was really, really interesting. We have 2 questions so far. So are there any locational or physical barriers to this project in terms of areas that the robots perhaps can't assess, maybe due to legacy sections of the network, or maybe the pipelines are too narrow?
Definitely. So great question. So really the physical barriers would be related to just the size of sensors. And so as you can imagine, the size of sensors can preclude it from accessing very small pipe sizes. So that may result in kind of a different technical approach. Or, you know, conversely, if there are reducers in pipes or things like that. But generally, for the latter, there may be opportunities to just structure, you know, the deployment or the excavation in a manner such that the robot can travel from the smaller pipe into a larger pipe.
Yeah, no, really good. And perhaps an opportunity to link up with maybe other projects who are looking at maybe sections of smaller pipelines and things like that, and sharing learnings there. Brill. So the second question is, can you outline the innovation in this project in terms of what are the significant risks that are needed to be overcome? And why can't this be adopted as business as usual yet? What is the process there?
So I guess the innovation, I guess the core challenge here is the work associated with two gas networks to perform this level of mapping is very intensive and very disruptive. And so, as I mentioned earlier in the call, the 74,000 kilometers of pipeline to inspect that with pushrod cameras, that's a lot of inspections. That's a lot of, essentially could be knocking on people's doors, accessing their basement or accessing their meter box. Very disruptive, very costly. So kind of the overall goal here is how can we make this tetherless autonomous robot inside the pipe, send it inside the pipe and potentially allow it to map for some extended period of time, to thereby kind of capture a greater portion of the network with limited disruption to consumers. As far as its use as a kind of, or its potential as a business as usual project, the challenges here, there are technical challenges here. So this is for example, 3D mapping and things like that. This is too high of a risk profile, I would say, for most BAU projects. And so that's why it's best suited, generally speaking, for SIF, who is looking for kind of these innovative, transformative projects.
Thank you so much. We still have a little bit of time. So just because this is my area of interest, so there exists quite a few robots, I would say, that are simply one device which travel through either tethered or untethered. So what's the actual benefit of having two side by side going through simultaneously?
That's a great question. But so really the I guess the proposed approach here for the multi-robot system is a result of some challenges in the mapping technique. So in the case of some of the pipes, there just are not a lot of kind of visual features inside the pipe, and so we kind of generate this visual feature to be able to more effectively map the pipe. So if you could imagine, maybe old cast iron may have some features, but maybe plastic may not. And so to map this and be able to perform accurate localization, we just need some sorts of visual features to use as kind of key points as part of the mapping process.
Fantastic. Well, I think that will conclude the Q&A. Thank you so much for your presentation, Mersim. And I will do a quick wrap up and end this show and tell. Thank you so much.
Thanks for your time.
No worries. Thanks everyone for joining today. Have a wonderful rest of your evening. Can we go on to is there another slide with the rest of the show and tells? No, maybe not. Okay, our show and tells continue tomorrow. Here we go. So they continue tomorrow all the way through to the 21st of June. So keep an eye out. Tomorrow in the morning, we have improving system efficiency. And in the afternoon, we have asset efficiency and improvement. So keep track on all of the show and tells and look forward to seeing you in some more. Thanks, everyone.
Thanks, Beth.
Thanks, Beth.
Thank you.
Thank you.